Welcome back, everyone, to the One World Probability Seminar. And our today's first speaker is Tomas Berggren from the University of South Florida, and he's going to tell us about the Gaussian free field and discrete Gaussians in periodic timer models. Please.
Thank you, and thank you very much for the invitation. It's great to have the possibility to give a talk here at the World Probability Seminar. So as Mariana said, I will talk about the Gaussian free field and the discrete Gaussian in periodic dimer models. So this is based on joint work which is done with Matthew Nicoletti. And as the outline of the talk here, so I will start to talk about dimer models, which is the topic of my talk, and in particular talk about the Aztec diamond with periodic weights. And when I've introduced the dimer model I'm interested in, I will go on to the main topic, which is global height fluctuations, where I will state and discuss the main results of this paper or of this talk. And in the end, I might or might not, depending on the time, talk a little bit about the spectral data and the linear flow which come into this to the main results. We'll see if we get there or not. But, yeah. Part of this talk, I think, is somewhat technical. I try to make it accessible, but please feel free to ask questions when things are unclear. Okay, so let me first talk about the dimer model. So what is the dimer model? So in a rather general setting, you start with some planar bipartite graph, G over here. Or over here, I guess. A dimer cover of this graph is a subset of the edges of the graph, which we call dimers. And this subset is such that each vertex of the graph is covered by exactly one of these dimers. So here in this picture, the blue edges here are the dimers. For a dimer model, you want to introduce the probability measure on the set of all possible dimer cover of the graph. And to do that, we introduce a weight function, new here. And the weight function associates to each edge positive edge weight. Okay, and then you define your Gibbs measure simply by saying that the probability to see a certain dimer cover is the product over this weight function, where the product runs over all edges in the dimer cover. And then, of course, we normalize by a normalizing factor to make it a probability measure. And the normalizing factor is called the partition factor. A few times in this talk, I will show you a number of pictures in this talk, and to do that, it's kind of convenient or kind of nice to think about these dimer covers as tilings. So what you do is to think about this as a tiling. You simply look at the dual graph, and instead of a dimer cover, you have a tiling of some region, and the tile in this setting is then the union of two adjacent faces of the dual graph. And the game is, instead of finding a dimer cover, you find a tiling of this region, where the tiling is you tile the entire region such that no two tiles overlap each other. But as I said, this is only for the sake that it creates nicer pictures. So to discuss this height fluctuations, which is the topic of this talk, it's we want to talk about the height function. So to a dimer cover, you can actually associate a height function. I will come back to this a little bit later. So instead of thinking about these as random dimer covers, you can think about these as random height functions. And it was proven, like, a very important and early result in this field done by Kenyon, Okonkov, and Prop over or almost 25 years ago now, says that if you have a sequence of bipartite graphs and this graph converges in some appropriate sense to some region R, then the normalized height function converges to a deterministic limit, which we call the limit shape. So this is a type of law of large number result. And in this talk, I would be interested in how the height function fluctuates around this limit shape. So this is a type of law of large number result. So how does the centered height function fluctuate as the size of the graph tends to infinity, or equivalently when the mesh size of the graph tends to 0? So that's what I'm interested here. And I will not, now I've been rather general, but I would be interested in a very specific graph, namely the graph known as the Aztec diamond. So this is, so here to the left here, you have the graph known as the Aztec diamond. It looks like this. This is the Aztec diamond of size 4 because it has 4 vertices on each side, right? And like this. Here as an example, I have, you saw this before, you have a dimer cover of the Aztec diamond, and here is the corresponding tiling, domino tiling of the Aztec diamond. And when I show you this picture, I will colors the different colors the domino tiling, the tilings in 4 different colors, and I will do it in I will color them in yellow if you have a vertical domino tiling with the white vertex pointing upwards, and in blue if the white vertex is pointing downwards or is down. And then I will color them in red or green, depending on if the white vertex is to the left or right for the horizontal dots. Okay. Right. So if you start with the easiest possible probability measure on this graph, namely the uniform measure. So you take this weight function simply to be 1 on all edges. Then you can see this very clear structure emerging. So here I have generated a random sampling of the Aztec diamond of size 10. Here I think it's maybe 20. Here it's probably 100, and here 300, I think, or something like this. And I should say, maybe you can see I rotated the Aztec diamond by 45 degrees. So instead of like a diamond, it looks like a square now. Yeah. Okay, so what do you see in these pictures? Well, okay, at the first, when you have a very small Aztec diamond, maybe you don't see so much, right? But as the size increases, you see this structure, right? So you get these regions at the corners where you only see one type of these dimers. And then you have something which is close to a circle, and inside the circle, you have a more disordered region. And this is a very famous and old, classical result by now, that as the size of the Aztec diamond converges to infinity, or the mesh size goes to 0, the boundary between what we call these frozen phases and the rough or liquid phase converges to a circle. So this disordered region converges to a disk. Right, and then I said I wanted to come back to a more precise definition of these the height function. So there are slightly different ways to define this height function, but I think this is the easiest way to grasp it, at least if you see it the first time, maybe. So what you do, sorry. So what you do is that you choose a reference. You choose reference dimers. I choose, if you look at this picture on the right side, I choose these red dimers to be my references. And then for each dimer cover, so here I have one, I superimpose the two. In addition to the dimer cover, I also draw these red ones. So that's what I've done here on the right picture. And what you get then is non-intersecting path, starting on this side, ending at this side. So here you have a path, right? Going down here you have another path, here you have another path. Also, if you have a dimer and a black and red dimer together, I just ignore them. So now you think about the height function by setting.
Question.
Yes.
I have a question. Your reference configuration, is it the one in the whole plane, or what is the reference configuration?
The reference configuration is not in the whole plane. It's simply in the Aztec diamond. It's all the north edges, which I colored in red here, in the Aztec diamond.
Okay, so it's not a perfect matching of the diamond.
No. So for me, here I don't take the. You could also take any reference diamond configuration, right? But then you would have the boundary condition to be 0 everywhere. Here, when you don't take a dimer cover, like when you don't use true dimer cover as your reference matching, then you will get this path instead.
Okay.
Right, and then you set your value of the height function. Maybe I set the value of the height function to be 0 here in the corner, and then simply every time I have to cross one of these paths, I increase the value by 1. So I cross a path here, I get the value 1. I cross a path here, I get the value 2, and so on and so forth. And that gives me the height function. Okay, and so if I take a large Aztec diamond now, the height function will look something like this. So this is I plotted the height function from 4 different perspectives, just to give you kind of a sense of what it looks like. And you see that you have these like flat regions in the corners, which corresponds to the frozen regions, and then you have this like a curved region, which is the rough region. Maybe I can show you an additional thing, because it's kind of nice. So this is a web page done by Alexei Borodin together with his son, and here you see the Aztec diamond with uniform weights, random sampling, and now you can actually make it. You should be able to make it 3D. So I just rotate it a little bit, and now you see the height function. And yeah, as before, you see the frozen part, which are the linear part of the height function. Then you have the curved part, which is the rough region. Right. Okay, so that's somewhat of this the short story about the uniform case. But I'm interested in the case when we have doubly periodic weights on the Aztec diamond. So to do that, I define my weight function, right? And maybe the easiest way to do it is by defining the weight function on what we call the fundamental domain. So you choose some subset of the Aztec diamond, the one I colored in red here. I will always, in this setup, I always take the fundamental domain to be a rectangle of this type. So this, I guess, is a square, but you can continue it either like this or higher like this. And this fundamental domain, or I say that this weight function is k-periodic in the vertical direction if the fundamental domain has two black vertices on the k black vertices on the left, and it's L-periodic in the horizontal direction if it has L white vertices at the bottom of the fundamental domain. So I define my weight function on this fundamental domain, and then I just copy it, like I translate this fundamental domain throughout the Aztec diamond and define the weight function in a periodic way by simply moving this fundamental domain. Right, and okay, this might not be, if I take the Aztec diamond of size n, there might not be a integer number of fundamental domains. I cannot cover it exactly. So for simplicity, I would also assume that the Aztec diamond is of size k times L times n to make it easy. So given this weight function, the probability is now the Gibbs measure I showed you at the very first slides, right? So the probability of a diamond cover is just the product over this weight function. So what happens when you consider that probability measure? Well, here I sampled a few examples of this, and what you kind of can see is this this limit shape phenomena I mentioned in the beginning. So the law of large number type of result, namely that, so here on the first image, I have chosen 2 times 2 fundamental domain with some weights of some sort. And with very high probability, if I make a random sampling with that weight function, I will see a picture looking something like this. So similarly to the uniform case, you will see this in the corners. You will only see one type of diamond, right? So you see these frozen faces at the corners. Here you will, if you look carefully, there is actually some more frozen regions here where you have more than one type of dimer, but they are still frozen. And then you have what we call the Arctic curve, separating these frozen pieces with this disordered or rough region inside here. And maybe you can see even inside here, there is in fact a third region. Maybe you can see it here. It's clearer in the other picture maybe. But this one we call the smooth region or gas region. So just to make it clear, so here I have chosen another fundamental domain, still 2 times 2, but it's with other weights, and you see you still have this frozen region, the rough region, and then one smooth region, but the picture is different, right? And down here I have a 3 times 3 fundamental domain, and here I also have a choice of 3 times 3 fundamental. And the names frozen region, rough region, smooth region comes from the Gibbs measure you are expected to see if you zoom in somewhere in this picture. And the translation, the ergodic translation invariant Gibbs measure were categorized about 20 years ago by Kenyon, Okonkov, and Sheffield, where they said that there are 3 types of Gibbs measure, or ergodic translation invariant Gibbs measures, namely the frozen ones, the rough ones, and the smooth one. where the differences between them is that the frozen is essentially deterministic. The rough region, the dimer-dimer correlation decays polynomially with the distance, while the smooth phase, the dimer-dimer correlation decay exponentially with the distance. And I proved together with Alexei Borodin a few years ago that these are indeed the Gibbs measure you see if you zoom in somewhere in the Aztec diamond. And that's why we call this the frozen region, right? Frozen, rough region, because in here you will see the rough Gibbs measure.
So Thomas, sorry if I interrupt. Going back to the first picture you showed us, which, I mean, it was just a circle. There,
yes.
So it looks like we have only liquid. Oh, okay,
Yes.
liquid in region 1, but no smooth.
Yes, and thank you for this question. That's a very important difference here. So traditionally, if you look traditionally, people have mainly looked at uniform measures on, if you look at Aztec diamond, or if you have some other favorite region, you look at the uniform Aztec diamond, because the uniform measure, because that's what you can do, and in that setting you only expect to see frozen and rough regions. This smooth region, at least for the Aztec diamond, only shows up in this periodic setting. So that's like one of the reasons why you are interested. I mean, of course, you get these more exotic pictures, but you also need to consider this periodic setting when to see this smooth region. Thank you. Right. Another thing is that, like similarly to the height function here, will have it will be flat at the frozen phases, but it will in fact be approximately flat at the smooth region. So I will show you another simulation or this web page again. So here there is an Aztec diamond of a periodic Aztec diamond, periodic weight. So you have these smooth regions here, and if we make the height function here, you still see this flat or linear frozen part. Then you have the curved rough part. But okay, it might be hard to see, but if you look carefully, there is in fact the smooth face is in fact linear as well, or at least approximately linear, which will be important for us in a minute. Right. Okay, so now let me continue to what is actually the topic of this talk, namely the height fluctuations of these models. So here, so as I said, I'm interested in the height fluctuations. I want to center my height function and see what is the behavior of this in the large end. And here I have a picture of, I've taken two samples of random, two samples of the dimer covers, random dimer covers, and I look at the height difference between them. And you see that at the frozen phases here, it's completely flat because it's essentially deterministic. You have the rough region in here where you know, it's kind of wild. You have a lot of fluctuations, and maybe you can see that inside here, like let's say here, there is in fact this corresponds to a smooth phase, and you still see some fluctuations, but it's much less, which is very important for us. Right. Right. Okay, and before I continue to discuss what we expect to see, let me just give a brief just recall briefly what the Gaussian free field is. So if you pick a domain in R2 and you let this curly G be the green function corresponding to the Laplacian, the Gaussian free field is a Gaussian process on this domain D with the covariance at different locations given by this green function. And using from Wick's formula, you can this kind of determines the higher moments as well. So if you look at the higher moments of this Gaussian free field, it has this form here. So it's a sum over pairings, and you take the product over this green function. And maybe I should say, I mean, I will not talk about this, but I mean, if the green function is singular on the diagonal, so I mean, defining it like this pointwise doesn't make sense because the variance it's not finite. So to really define it properly, you should talk about the Gaussian free field as a random distribution. But okay, let me not go into those kind of details here. Right, so that's just a reminder about what the Gaussian free field is. And it was proven in the uniform setting that if you want to describe the height fluctuations of the Aztec diamond with the uniform weights, you define, or there is a diffeomorphism going from the rough region to the upper half plane, such that the height fluctuation, the centered height function, converges to the Gaussian free field with Dirichlet condition in the coordinates defined by this diffeomorphism. And this fact is like this is one. So there is this very general conjecture, very important conjecture in the dimer community, namely that if you have some reasonable graph, you expect that in the limit the height fluctuation should always converge to the Gaussian free field in some conformal structure. And it has been proven in many cases over the year, but the general conjecture is still open. In our setting, it's not as simple. We don't, and why is that? So because now the rough region, where we expect the main contribution from the height fluctuation should come from, is now multiply connected, right? Because you have these smooth faces, which you didn't have in the uniform case, which was pointed out before, right? Okay, and there is, so we proved, so I proved together with Borodin, and it was later reproven with different method by Bobenko and Bobenko, that there is a diffeomorphism going from the rough region in the Aztec diamond to what we call okay, now I only say like the half of the spectral curve. For now, you can simply think about this, the half of the spectral curve, as the upper half plane with some holes in it. Okay, maybe at the end, probably not. I will tell you more what this object is, but yeah, okay, probably I will not have time to do that. But just for now, think about it like this. So here, there is a diffeomorphism from the rough region to half of the spectral curve. So here you should think, so this diffeomorphism, when you go to the outer boundary of the rough region, the boundary between the rough region and the frozen region, that corresponds to the real line in the upper half plane here, while the boundary between the rough region and the smooth face corresponds to the boundary of one of the holes. So each hole corresponds to a smooth face. So now you can expect, okay, so what should we see here? Okay, maybe we will see the Gaussian free field on this multiply connected domain, right? That's very natural to expect, right? But is that all? And before our paper, this was not known, but we had some hints or some, something to go on. So there has been some work where people have looked at similar questions. So, for instance, very importantly, is a paper by Ruskik and Van Pesky, where they looked at the dimer cover on a cylinder, and in a cylinder is like, essentially an annulus with a hole in it. And in that case, in addition to the Gaussian free field on the cylinder, you also saw a discrete Gaussian appearing. And similar, there is some heuristics, where I have a picture here. So there is some heuristics for the hexagon with a hole in it. So here you have a lozenge tiling of a hexagon. And you see here, and here you have a hole inside the hexagon. So this is, this is a hole. You see then the rough region will be essentially an annulus and the hole with the hole in the middle, right? And in that case, you're at least heuristically, we know that then you will see the Gaussian free field with on this annulus with a discrete Gaussian capturing the height fluctuation of this hole. Because this hole, I mean, in this picture, maybe you can essentially see the height function, right? And depending on the dimer cover, the height of this hole will vary. And this fluctuation will be governed by a discrete Gaussian. So now if we go to the Aztec diamond, we also have, okay, here when we only have one smooth face, we have an annulus, which is the rough region is also kind of an annulus, right? And then the smooth face the question was like, does this behave like a hole in a similar way? And it's actually a rather delicate question because, I mean, the hole is completely flat, right? The smooth face is not exactly flat. So just to define the height of a smooth face is not easy, and it's actually very non-trivial. Right. But so our main result is really this fact that that what we will see is the Gaussian free field on this multiply connected domain, plus and in addition we will have these discrete Gaussian random variables which governs the fluctuations coming from the height fluctuation coming from the smooth faces. Okay, let me be a little bit more precise about this. So what we prove is that this height function, this centered height function for finite-sized Aztec diamond can be decomposed into two terms. One term, which I called h and tilde, and then one sum where g here is the number of smooth faces in the graph. Sorry. Right, G is the number of smooth faces in the graph. And we prove that in the large n limit, when the size of the Aztec diamond tends to infinity, this h and tilde converges in the sense of, on the level of moments, is what we prove it, is how we prove it. So on the level of moment, the h and tilde converges to the Gaussian free field on the rough region under the conformal structure defined by this diffeomorphism, which I mentioned before. Moreover, this FIN, these converges to harmonic functions on the rough region with zero boundary condition everywhere except at the ith smooth region where it has the boundary condition 1. And then this ZIN is a vector, and this vector converges to a mean subtracted discrete Gaussian vector. Okay, and in addition, we show that in the limit, this term and this term are independent in the limit. So, okay, let me rephrase this again. So what we prove is that in the limit, the height function converges to the Gaussian free field on a multiply connected domain, plus a harmonic function with boundary condition on the smooth faces, with random boundary conditions on the smooth faces, and this random boundary condition are governed by a discrete Gaussian vector. Okay.
Thomas, can I ask? So no assumption essentially on the weights.
Yes, there is some assumptions on the weights. But very few actually. So you take this periodic. You start with this periodic setting. We do assume that the size of the Aztec diamond is k times L times n, where the fundamental domain was k times L. For generic weights, the number of smooth faces in the Aztec diamond will be k minus 1 times L minus 1. But this will not happen for all set weights, but generically this is true. And we do assume that this is the case. That's the assumption we put on the weights.
Okay, generically, intuitively, maybe means that, I don't know, they are IAD or like what would you? I mean, of course, they cannot be like all the weights equal. So generically, they means that there should be enough inhomogeneous.
Yes, exactly. I mean, okay, so this comes down to, I mean, it's very like it's kind of hard. You really need to specify your weights rather delicately to see for the number of smooth faces to drop. And the easiest way, and unfortunately, I will not have time to go into this, but what you look at is the spectral curve. You can associate the spectral curve to this fundamental domain. I mentioned this before, but I didn't go into it. And the genus of the spectral curve is generically k minus 1 times L minus 1, but there is ways for this genus to drop. And that's how we can see it.
Okay.
Yeah.
Thank you.
I see that there are a few questions in the chat. Should I? That was okay. That was not. Okay. So the rest of the talk, which maybe it's not so far, but so much, but. I will simply try to describe these results in more details, to explain them in more details. So the first question is, how do I define this ZIN, right? The part which should capture the height of the smooth faces, or rather the height fluctuations of the smooth faces. And I mean, as I said, these smooth faces are not exactly flat. Here I've zoomed in at I looked at the fluctuations, some small region in the smooth face, and you can see that it's essentially flat, but it has these spikes, so it does fluctuate a bit. And what we want to do is simply to remove all these spikes, right? So we want to, intuitively, CI should just be, the height, or maybe the height, the mean subtracted height. But that's not so easy. So what we do instead is to take an average. So we define this CI as a spatial average of the height function in the ith smooth phase. So more precisely, we take some grid, some mesoscopic with a grid with mesoscopic spacing in the ith smooth phase, with the number of vertices being m, where m is much smaller than n, but still much larger than n, much larger than 1. And then we define CI as this average over all vertices of this grid, or all faces in this grid. Okay, and the idea is that, okay, you have these spikes, right? But on average, this one will cancel out. So this should capture, you know, in some sense, the height fluctuations of the smooth phase. So that's how we define this. And okay, the exact way is not important, right? But this is how we do it. And for technical reasons, this is a convenient way to define it. Okay, and then, okay, this is a bit of a mouthful of a slide, but let me try to explain it. So now I define these ZIs, right? And then I also want to define this FIN, which converges to a harmonic function, right? So one way to do it is simply to define the harmonic function on the rough region in the way as I want the limit, and then I simply discretize it. Okay. And okay, at the end, remember that I want this equality, right? So now we simply defined hn tilde from this equality. So I move, you know, this sum to the other side. So I define hn tilde by this difference, where I remove the where I have the height function and remove this big sum, right? So what we now prove is that if you let g here be the Green's function on this, you know, the half of the spectral curve, and I fix some points, r points on this this r naught, such that that under the, and I take, if I take this limit where and I take FIN here to be the phases such that under this diffeomorphism we had, it converges to these points, then the higher moments of this hn tilde converges to the higher moments of the Gaussian field. Maybe you recall this is exactly the formula for the higher moments we saw at some earlier slide for the Gaussian field. So we prove this is the limit we prove. And we also prove that in the limit, the higher moments of hn tilde and the ZJN, they become multiplicative in the limit. So this difference here converges to 0 for all integer nj. Okay. Right, and then I also want to say, so that's one part of it, right? So that's this part, right? This part together with this part. Now I also want to say so just this fact, right? That this CIN converges to the discrete Gaussian random vector. So just as a reminder about what is a discrete Gaussian, for a discrete Gaussian you need to G vector, so you take E and RG, and you take tau should be a purely imaginary matrix, G times G matrix, such that the imaginary part of tau is positive definite. And then we say that this vector x1 to xg is a discrete Gaussian vector if it is distributed according to this rule, right? So the probability of x is equal to x is e to the I pi times x minus e times tau x minus e. So you can see this is very much how the usual Gaussian is distributed, right? But now x is in ZG. Okay. So what we prove, maybe this is the last thing I say. So we prove that, or what we do is that we determine some vector E0 and t in Rg and this tau, such that if we let xn be distributed according to be a discrete Gaussian, determined from tau and this shift vector En, which is n times E naught plus t, then the higher moment of this Cjn converges to, or is approximately equal to, the higher moments of this discrete Gaussian. And I should say that, I mean, I have included an n even in this limiting objects, and it's because this E do depend on n, right? So the real convergence actually only happens on subsequences. So like, yeah, the moment convert, because I mean these are still n dependence in the limit. So the convergence only happens along subsequences. Right. But it's in this sense we prove that this Cjn converges to the discrete Gaussian vector. And maybe it's an appropriate time. Yes, exactly. So maybe it was a little bit rushed here at the end, but I think that's an appropriate time to end. But let me just say again that we also really describe this tau, t, and E naught in terms of some spectral data from the diamond model, which is also a very interesting part of this project, but that will be for another time, I think. Okay, so yes, thank you for that.
Okay, thank you, Thomas. If you have a question, please just raise the, please press the raise hand button on Zoom and we will unmute you.
Maybe meanwhile I can ask a question. The result you told us is not really sensitive to the way you define the height function, or is it?
Sorry, say again.
So the result you showed us is also not so sensitive to the definition of height function that you give. So
no. You're absolutely correct. I mean, here, I mean, and to be honest, which I wasn't really in the talk, my exact definition of the height function or the picture I've given here in the talk is not really, I haven't cared really about my precise definition of the height function, because this definition I gave you here doesn't exactly produce these pictures. It's like a deterministic linear transformation between the two. And exactly as you say, no, that was in the wrong direction. Exactly as you say, the left-hand side here, since I subtract the expectation, this is not the precise way I define this height function is not relevant here, where it's independent of the choice of reference matching.
Thank you. There is a question from the audience.
Yes, thanks. I hope you hear me. I'm out of the office. The question is, thanks for the lecture. You mentioned random matrix theory at the very end. Are there any concrete random matrices that the discrete Gaussian things and things that you explained can be transferred to the dimer model and things that you presented? Thanks.
Thank you. Yeah, so, right. So I guess I didn't really mention it, but you were observant and saw that I had written it, right? Now I can't find it. Sorry, I'm confused here. So you're referring to this one, right?
The last, yeah.
So yeah, so what I'm referring to here is that in random matrix theory, you can sometimes have, if you're like, I mean, you look at maybe you have your eigenvalue of this random matrix of these random matrices are maybe, you know, supported on, let's say, 2 intervals. You can have more than 1 interval, but let's say 2. Then there is this, if you look at this eigenvalues, the number of eigenvalues in each components are not fixed, right? So there is this like probability that an eigenvalue jumps from one support to the other support. And to my understanding, this is governed by also like a discrete Gaussian. And apparently, okay, and this, don't push me on this, but there is similar storylines if you look at you know, particle system on the complex plane, maybe, you know, more, yeah, then you also have these jumps, if I understand. I'm not aware, and I don't think there is like a direct relation, as you suggest, that you can actually phrase this in terms of random matrix theory. This I'm not. I don't think that. Yeah, I'm not aware of such thing, right? Yeah, I mean, in dimer models, you can see a random matrix, and that's really when you look at the touching point where the liquid, the rough region touch the boundary of the Aztec diamond. Here you actually see the GUE minor process. I don't. Okay, I have to think if you can. I don't think, but yeah, I don't think that will yeah, come into play in this. So no, yeah, I don't think so.
Okay, thank you. Thanks.
All right, any other questions? Okay, if not, thank you, Tomas, again. And let us have a tiny break. Federica, how long do we want to have a break?
Should we start, Mariana?
Yep.
Yeah. Béatrice, you
Yes.
ready?
Okay. Great. So, well, first of all, thank you very much for the opportunity to give a talk in this seminar. That's really nice. So yeah, I will be talking about Fock's dimer model on the Aztec diamond. And this is based on joint work with Cédric Boutillier, who is in Sorbonne Université. So, well, of course, we're paired with Tomas, so it's on the same topic. And so some of the slides will be kind of similar, and then the topics will kind of move apart, but there's some common topic in these two talks. So here is an outline. So I will tell you about the dimer model on the Aztec diamond. So this is strictly like in Tomas's talk. And then I will tell you about something that we haven't seen. It's Fock's weights. So we will consider the dimer model with a specific kind of weights, which are called Fock's weights, and which I will define. And then I will tell you about the main result of this work, which is an explicit formula for the inverse cancelling matrix, which you will know more about in a few slides. And then also I will tell you about another result, which is about the partition function of the model that we have a recurrent formula for. And then I will show you a few pictures about limit shapes. Yeah, so you will see. Okay, so the Aztec diamond, I don't know if can you see my mouse if I move on the screen or not? Yes, okay, great.
Yeah.
So this is an Aztec diamond of size n, okay, so n here in this case is 4. And so it's just a sublattice of the square lattice, which with a kind of tilted boundary. And so on this lattice, on this Aztec diamond, we will consider dimer configurations. So a dimer configuration is also known as a perfect matching. And so it's a subgraph of our graph consisting of edges such that all vertices have degree 1. Okay, so every vertex should be incident to exactly one edge. So here in green, you have an example of a perfect matching. And then we put weights on these edges, which are parameters for our model. And they're represented by a weight function, which is denoted by nu. So every edge E has a weight nu of E. And then once you have all of this, you can define a probability measure on the set of all dimer configurations known as the dimer-Boltzmann measure. And it's defined as follows. So it's proportional to the product of all the edge weights that are in the dimer configuration. Okay, so typically if an edge has a large weight, it will be more likely to be present. And so quantity of importance is the normalizing constant. So it's the sum over all dimer configuration of the weights of the dimer configuration. It's what you need to make it a probability measure. And it has a name, it's a partition function. So in statistical mechanics, the dimer model represents the adsorption of diatomic molecules on the surface of a crystal. Okay, so this model came from the chemist community and was very much studied in the physics community, and then now also in the mathematical community. And so in statistical mechanics in general, this normalizing constant of the Boltzmann measure is important, and so it has a name. It's the partition function. It's important because it contains already some information on the macroscopic behavior of your system. Okay, so that's the dimer model. Okay, and so our goal is to do computations on this model, and so there's a tool, a key tool to do computations, which is known as the Castellane matrix. So now I will tell you how this matrix is defined. So as you have seen, our set of vertices is bipartite, meaning that you can color them in 2 colors so that a white vertex is only incident to black and vice versa. So the set of vertices is naturally split into black and white. And then we need to assign to every edge a modulus 1 complex number, which we'll also refer as a phase. So it will be phi WB. So an edge now can be indexed by a white and a black vertex. So that's an edge WB. And so phi WB is a modulus 1 complex number. And we assign them in a specific way, so such that when you take the alternate product of the phases around a face, you get a -1. And so it's a theorem of Castellane, then extended by Kuperberg, that it's always possible to assign such a complex phase. So of course, for just the square lattice, it's easy to do by hand, but there's a general theory for planar graphs, okay? And so in general, you can always assign such modulus 1 complex numbers. Okay, and so once you have these numbers, you can define the Castellane matrix. So it's a weighted adjacency matrix of our graph, so the Aztec diamond. So every edge, so it has rows indexed by white vertices and columns by black. And it's an incidence matrix, adjacency matrix, in the sense that you have non-zero coefficients if and only if you have an edge. And then it's weighted because usually in an adjacency matrix, the coefficients are just ones. But here they are the weight of the edge times this complex phase. Okay, and so this tilde sign just means that W and B are adjacent in the graph. And otherwise it's 0. Okay, so here I've just drawn on a little example, the Castellane matrix of this small graph. So you have 2 white, 2 black, so you have a 2 by 2 matrix. we have a weight function A, B, C, D. Here, the 1, 1, I are the complex phase that satisfy this condition. And so this is simply the Castellan matrix. And so what you see on this small example is that when you take the modulus, well, in our case, it's just the absolute value, but when you take the modulus of this determinant, you get AB plus CD. And if you look at what happens here, you have, on this graph, you have two dimer configuration, this one, taking opposite edges, and this one. Do I have a picture? No. And the other one. And so the first one has weight AB, and the second one has weight CD. So here it's the weighted sum of dimer configurations of this graph. Okay. So that's only on an example, but actually that's a theorem. So by Castellan, Temperlin, Fisher, if you just take as complex phases numbers plus or minus 1, but we need something a bit more general. So these complex numbers, modulus 1 complex numbers, and so that's an extension due to Kuperberg. So the theorem states that actually the partition function of your model is the modulus of the determinant of this Castellan matrix. So this was quite a remarkable result. It's not all models of statistical mechanics where you have an explicit expression for the partition function. Actually, there are a few of them. There's only Dimer's, Ising model, and spanning tree, spanning forest, basically. Okay, and so as a corollary of this result, Kenyon proved in 1997 that the probability of all dimer configurations containing a fixed subset of edges, so you consider k edges, E1 to Ek, with vertices W1, B1, WK, BK, and you want to know the probability of all dimer configurations which contain this fixed subset of edges. Well, this also has an explicit formula, and it's given by the product. This is basically the product of the edge weights times the determinant of the inverse Castellan matrix, restricted to columns corresponding to black vertices of this set, and that's rows, sorry, and columns corresponding to white vertices of this set. Okay, so you take the inverse of the full matrix, and then you restrict it. So this matrix is a K by K matrix. Okay, and this you can see the proof of this result is you count the number of plausible configuration divided by the sum of possible configuration. You compute this using the determinant, and you use the Jacobi formula relating the minus of the matrix to the coefficients of the inverse. That's basically the idea of the proof. Okay, so the bottom line of this slide is that if you want to understand the dimer model, anyway, the starting computations, you know the partition function if you know the determinant of this matrix, and you know how to compute edge probabilities when you know the inverse of the Castellan matrix, okay, the determinant and the inverse. Okay. Now to proceed, I need one more notion, and that is that of gauge equivalence, which I think was introduced. Well, of course, this notion was around in the physics literature for many reasons in different fields, but for dimer model, probably this was introduced by Kenyon, Okunkov, and Sheffield in 2006. And so the idea is the following: is you have a weight function on your edges, and say I take another weight function. Are the models really different, or are they the same from a probabilistic point of view? And so actually, yeah, so weight function on the edges is you have too many degrees of freedom. You need actually only degrees of freedom per faces. So let me, I think now give the definitions. So two weight functions are gauge equivalent if for any face, so in our case, it's just square faces, so it has 4 vertices, the alternate product around the face is the same. And so when this is the same, there are two things. So first, the partition functions are explicitly related. So they're equal up to a global constant. So that's the weight with one weight function of a reference, any dimer configuration, divided by the weight of the same dimer configuration with the other weight function. Okay, and so of course this, it's not clear when you just look at it, but this quantity is independent of the choice of M0. And why this is true that it's independent of n0 because of this condition. Okay, you have seen superposition of dimer configurations in Tomas's talk. So that's the underlying idea. And so if this condition is satisfied, so this gauge equivalence, then you have the same Boltzmann measure. Basically, these constants cancel between the numerator and the denominator when you take probability measures. Okay, so the real notion to have a Boltzmann measure, the real degrees of freedom are these alternate products around faces. Okay. So now we also see pictures that we have seen in Tomas's talk. So the diamond model on the square grid, or specifically on the Aztec diamond, is in bijection with domino tilings. So here I drawn the dominoes. So actually you should start from the dominoes more. You see here, you have another square lattice in gray. And in the middle, you always put a vertex of your Aztec diamond. You join these vertices whenever you have an edge here. So basically it's the dual graph, but then you have to be careful on the boundary. It's the dual inside, and on the boundary it's a bit different. And so the bijection goes as follows. You take, whenever you have a diamond configuration, you join the two corresponding squares. Okay, and so that gives you a domino, which is a tile made of two squares. Okay, that's a domino. And so just by the perfect matching diamond configuration definition, you can see that you exactly have a domino tiling, meaning that you have no holes and no overlaps of dominoes. That's every vertex is incident to exactly one edge condition that phrases in no hole and no overlap in the tiling language. Okay, so this is the bijection without the underlying graph. And so here is the coloring, in the same way you've seen this in Tomas's talk. So you see that we have dominoes oriented in two different directions. And so here, for example, we have the green and the red and the green, and then the blue and the yellow. And furthermore, you see that some have a black vertex on the top and some have a white. And so that gives a different color. And so that's how you get 4 colors. Okay, so you distinguish between them. Okay. So diamond model on the Aztec diamond is a long history. Okay. So people have considered different kinds of weights. So starting from uniform, so every edge has the same weight. Then you have 1 periodic, then you have 2 periodic, you extend the period, 2 times k periodic, L times k periodic that are generic. I'm not going to insist on a generic. And so people were interested in enumeration first. That was kind of the first question. Can you count the number of domino tilings of the Aztec diamond? Also having explicit expression for k-1, as I said, this allows you to compute probability. And once you have these information, you're interested in taking limit shapes, which is what happens when you take the scaling limit and more. As you've seen in Tomas's talk, you can wonder about fluctuations around the limit shape, for example. And so here is it's always difficult to do lists because it's always risky. You might forget people, but at the same time, I think it was fair to cite some of the many people that worked on this subject. So there's, of course, Elkis, Cooper, Reg, Larson, and Prop, Yokush, Prop, and Shore that were the first limit shape result enumeration results. Then Heathcote probably had the first explicit expression for an inverse Castellan matrix. Then there was Johansen, Cheetah, Young. There's also a paper by Boutier, Chapuis, Cortel, and Ramasamy. And then there was a new approach, as you will see in 1 or 2 slides, that was introduced by Deutz, Kirch-Lars, and then Berggren and Brodin, and then different permutations of these authors. And also on the limit shapes, you had many results by Korn, Kenyon, Prop, Okunkov, Reshetekin, Kenyon, Okunkov, and also a new very nice result of Astala Duze Prausezon, Kenyon Prause, and also now by Bobenko. Okay, so that's part of the history on the Aztec diamond. Okay, and so here you see a limit shape result that you have seen many in the previous talk, and actually that's a picture of Thomas. So thank you, Thomas. And so, yeah, so I think I'm not going to insist too much on the limit shape, but you see that you have different kinds of behavior occurring. So you have like a big circle, and here you also have like a shape in the middle where you have a different behavior in the middle. So this should be 2 times 2 periodic weights. Okay, and so also there were people from many different communities tackling these questions. So you have a very large array of techniques, which is also very nice. So there were shuffling algorithms, and then it was proved that there's a connection to lattice paths and particle systems. So there's also people from that community who worked on it. Then also from combinatorics, so there's also the generating functions approach. Then it was also proved that there's a connection to Schur processes. So these models are quite rich because they seem to be connected to many others. And then of the new techniques that were introduced are the matrix-valued orthogonal polynomials and the block-tuplets matrices and Wiener-Hopf factorization. So that was like the Deutsch, Berggren, and onwards techniques. Okay. So what I'm going to propose in this talk is yet another technique to tackle these questions. So of working with the model in the discrete. And that is to parameterize the weights, the weight function in a specific way that is kind of I would say the book proof way of parameterizing the weight so that you can really see the structure coming out. Okay, so it's not the easiest parameterization, but once you parameterize them in this way, the formulas all look very natural. Okay, so that's the bottom line of this talk. So now I will have a few slides explaining how we write down the weights. Okay, so we need some background to do this. So the first tool that we need is some geometric data and theta functions. So we consider a maximal curve. So a maximal curve has an anti-holomorphic involution. So here it's so that means that basically you can do complex conjugation on your curve, and which has some genus, so some number of holes. And so the real locus, because you have a maximal curve, your real locus, which is the intersection of the curve with R2, consists of G plus 1 circles. Okay, so here you see you have 1, 2, 3, and then you also have the outer circle. So you pinpoint one of them, you call it A0, and then you have another 3 circles. Then we need, the Jacobian variety of the surface, which is kind of it is a G complex dimensional torus. And so it's defined, it kind of encodes some periods. So on this surface, you have some holomorphic one forms, and so they have some integral around the non-trivial cycles of your surface. And so this defines, in particular, some of the integral defines the period matrix omega. And so this is the Jacobian. And then, so once you have this, you can define theta functions on the G-dimensional complex plane. And so they're defined as follows. So it's just it's a sum of exponentials. It has the period matrix in it. And then that's a bit, so if you're in genus 1, it's kind of okay. But if you're in higher genus, the surface and the Jacobian don't have the same dimensions. You need a map to bring you points from the surface to the Jacobian, so that, because you want to have a theta function on the surface and not on the Jacobian, basically. Well, the Jacobian is this cut, but anyways, that's the idea. And then you also need the prime form, which is like building. We will need to have meromorphic functions on sigma, and so the prime form is like the building block of meromorphic functions. Okay. So that's one, I will show you examples as we get along. So that's one type of geometric data, which is really compact Riemannian geometry. And then we have some data that comes from the graph, okay? So geometric, but only from the embedding of the graph. So for like a few moments, we nearly forget the underlying surface. So on this Aztec diamond, you can draw what is known as the quad graph. So you put a vertex in the middle of every face, and you join this vertex to all the vertices on the boundary of that face. And then you consider the dual of this graph. So these are, in the Aztec diamond case, it's kind of really simple. It's just paths going vertically and horizontally, okay? And actually, you can orient them so that they always have a white vertex on the left. So this is oriented in this way, and so this one is oriented in this way. So actually, they alternate between arrows up and down, arrows up and down, okay? So you have 4 families of train tracks. They're called train tracks. And so to each such train track, we assign an angle, which is a number that takes values. So now we have to use our surface, A0, the cycle that was singled out. So we take points on this circle cycle. Okay, and so there we have 4 set of parameters: the alphas, the betas, the gammas, and the delta. So depending, you see, on the 4 family. Okay, and then we need another tool which was introduced by Fox, which is a discrete Abel map. So it's kind of a map. So it's a map on the blue vertices. So on these vertices, these here, and it's defined as follows. You fix a reference vertex, and then okay, it's defined on the blue and also on the vertices of the original lattice. And so every time you cross a train track, you either increase or decrease by the value of the parameter of this train track. And whether you increase or decrease just depends on whether it goes from left to right or right to left, okay? And so in this way, you can check that it's well defined so that you can go from any point to any point using any path. You will get the same value once you fix a reference point. Okay, and the last thing that we need is a point in the Jacobian, on the real locus of the Jacobian. Okay, and so once you have this, you can introduce Fox weights. So they were introduced by Fock in a paper of 2015. So actually, it's Fock's adjacency matrix. It's defined as follows. So if you want to know the Castellane coefficient of an edge WB, so here I've drawn an Aztec edge, you have 2 train tracks, alpha and beta. You have 2 faces, F and F prime. So you take the prime form evaluated at alpha beta, divided by the theta function evaluated at this parameter t, plus the value of the discrete Abel map at the point F, and then theta t plus the value of the discrete Abel map at the point F prime. Okay, so that's a very nice explicit formula. So that's a complex number, okay? So that's why we needed to have these complex phases. So it's a complex number. And so you want to know, well, does this define a Castellane matrix? Does it correspond to a Castellane matrix of some positive weight function? And so this is some work we did with Cédric Boutier and David Simazzoni that give you condition on the construction to indeed be a diamond model with positive edge weights. So the first criterion is that sigma should be a maximal curve. Then the angle map, so this value on A0 should have some order preserving property, okay? So all the alphas, so you have a cycle, so you have a cyclic order notion. And so all the alphas should be before all the gammas, that should be before all the betas, that should be before all the deltas, that should be before all the alphas, okay? And then all in between the alphas, they can do whatever they like. But you need to have packets of angles, packs of angles. And the point T should be on the real locus of the torus. It cannot be anywhere on the torus. And so what we proved is that if these conditions are satisfied, then a Fox adjacency matrix is indeed a Castellane matrix for a dimer model, okay, with positive weights. So we are indeed doing probability. So actually what Fogg did is that he introduced these weights to parameterize algebraic curves in general, with no guarantee of having an underlying real dimer model. Okay, in general, you have more general things coming. So we're kind of doing this very general thing in this positive weight framework. Okay, so some examples. In genus 0, so when you have no hole, sigma is the Riemann sphere, and so A0 is just a circle. The Riemann theta function in this case is just 1, constant function 1, and the prime form is v minus u. So, okay, so everything gets very easy. And you can map the circle with, well, the trigonometric circle. So you write alpha as e to the t I alpha bar. And so when you write down Fogg's weights in the genus 0 case, what you get is here you really see the phase I to the e I alpha bar plus beta bar. And then you have the weight, which is 2 sinus beta minus alpha. Okay, so it's like a trigonometric parameterization of your weights. And so these weights were known at least 15 years before Fogg's weights. Okay, they were introduced by Kenyon as critical weights for the dimer model. So he proved that the model behaved in a critical way when the weights were as such. But they were, yeah, so he kind of guessed this with this trigonometric formula, but outside of this more general Fogg framework. Okay, in genus 1, so your surface is a torus. So you have a modular parameter tau, which if the curve is maximal, it is in pure imaginary plus. A0 is just a circle. The Riemann theta function, so the one we're using, there are 4, but the one we're using is theta, the theta function theta 3. So those of you who know theta functions in genus 1, there are 4 of them. Either they're written as theta 1, 2, 3, 4, or 0, 0, 1, 0. Okay, there are different ways of writing them. And the prime form is given by the theta function theta 1 up to normalization. Okay, and so in this case, so the prime form is also a theta function. And so the formula is just this one. Okay. And that's in genus 1. Okay. So, of course, it's kind of, we say we parameterize the weights in a different way, but does it make sense to do this? And so this is the first thing we checked, is that actually whatever your weight function on your Aztec diamond, you can always reconstruct an M curve for some genus, find a parameter T, and also find angles. So on the circle A0, such that the dimer model with Fogg's weights is gauge equivalent to the other dimer model, the dimer model with the weight function mu. Okay, so these weights are not as esoteric as they may seem. But so this is kind of classical, uses just classical parameterization results of geometry. It's not, yeah, I mean, it's somehow it's known. It's existence results. Okay, so it doesn't tell you how to construct actually, how to construct the Fogg's weights once you know the other weight function. Okay, so I will show you examples where we did it explicitly. It still requires some work, a lot of work actually. Well, depending on how the genus and the number of parameters that you have. But anyway, in theory, Fogg's weights are as general as you may want. And okay, typically the genus will increase with the number of weights that you will have. Okay, so if you have uniform, you will have genus 0, you just have one weight for all edges, and the higher the period, the higher the genus, okay, generically. Okay, so here is an explicit example. So we worked out the 2x2 periodic weights of Borodin-Deutz. So there are quite a lot of things on this picture, but so here you can see the Borodin-Deutz weight. So here you have 1 over B, A, B, A, 1 over B, so it alternates. And here you have A over B, 1, AB, 1, A over B, 1. Okay, and then it repeats. So the period for this weight is called 2x2 because here in purple, you've seen I've drawn the period of the weights. And okay, and so here I'll show you how to parameterize it with Fox weights. So actually, you don't need all the Fox parameters. You can suppose that all the alpha are equal to 1 alpha, all the beta to 1 beta, etc. So you say you have 1 alpha smaller than a gamma, smaller than a beta, smaller than a delta. And you can also suppose that beta minus alpha is equal to delta minus gamma is 1/2. Okay. So actually what you have is 2 parameters. So you have, okay, here I've written it with Q. It's like tau. It's Q and tau are related. So Q is e to the I pi tau, I think. So you have parameter Q and you have parameter rho. Okay, 2 parameters are enough. Yeah, because you also have parameter T. So what we prove is that if you have the 2 by 2 periodic weights, the one I showed you with the A and the B, then you can always find a rho and a tau such that for a special T, the diamond models are equivalent. And so here is just to give you an idea of how you do if you want to do the explicit construction. Well, you have to take the alternate weights around faces and solve the equations. That's basically it. And so here we have 4 kinds of faces. Okay, so we have this face, this face, this face, and then it repeats. So we have to solve these equations. And so that's what we did. And it's useful to go through Jacobi's elliptic functions, which are constructed from the theta functions. And so this allows you to have an explicit relation between the two. Okay, so it's not even in this very explicit case, you see, it is explicit, but it's not maybe the most natural parameter. It's not the parameterization you would get if you just thought about it for a minute, right? Okay. So that's about the weight function. So now I want to tell you about our explicit expression for K inverse. Okay, so K is a matrix. Taking an inverse of a matrix, as you know, is a complicated procedure. If you want to know the coefficients of the inverse of a matrix, okay, it's not something that if you have a 1000 by 1000 matrix and I tell you what is that K minus 1, 10, 10, it's difficult to guess. Okay, so the point of this work was to give an explicit formula to for the coefficients of the inverse. And so they involve forms in the kernel of K. So K is it's a matrix, so you can see it as an operator. A form in the kernel means that when you apply K to G, Kg will be equal to 0 as a vector. Okay, and so how is G defined? So G is defined on vertices of the quad graph, but let's stick to the white. Yeah, okay, whatever. The vertices of the quad graph. So you have one vertex here, one vertex here, y, x, y, and you take a path from x to y, so along in the quad graph, okay, so following the gray graph. And so G from x to y is a product of increments, okay, along edges. So now I will tell you how to define these increments. And so the increments are defined as follows. So an increment, if you have GFW, if you go towards a white, it will be some theta function in prime form with a free parameter u. Now you have a complex parameter u. And if you go in the other direction, you take a -1. And from black to white to blue, sorry, F, then you have another formula, okay? It depends on whether it's white or black, but in both cases, it's implicit. And so you take the product of these functions along the edges, and that's defined Gxy. And of course, it's independent of the choice of path from X to Y. Okay. And these G do not come out from nowhere. Actually, they're at the heart. So this slide is the heart of all this parameterization. It's that the functions G are in the kernel of K, as I said, in the bulk, okay? Not on the boundary, in the bulk inside. Or if you have an infinite graph, it works as well. And why is this true? It's a consequence of phase trisecond identity. Okay, if you write down kg equals 0, you have to solve some equation, prove that some equation equals to 0. And why is this true? And that's because of this identity. So this, I think, is it's really much, it's an identity, and so it's written in genus G. If you write it in genus 0, this is an addition formula for sinus, okay? The one sine A plus B equals, so it's just a trigonometric formula in genus 0. But I think it's very important because it's the identity that is underlying somehow the reason why all these different approaches work out. So we haven't worked out all the link with all the approaches, but there's a miracle in the shuffling algorithm that makes that it works. And basically it's this identity. Also, I think in the Wiener-Hopf factorization, there's a miracle that occurs, and I think it's due to this identity. Okay, so that's the reason why this parameterization is really natural, because in all the techniques that work, there's a miracle, and that's actually the miracle. That's our belief. We haven't checked it in all approaches, but that's our belief. It's related to a spider move also on the dimer model. If you know about spider moves, invariance of the dimer model under spider moves, that's why it's true also. It's because of this identity. Okay. And so once you have G, now I can give you the formula. So the K inverse, so you have a Aztec diamond of size n. So the coefficient of the inverse between a vertex B and W is a constant times 1 over theta p. P is a specific point times a double contour integral times, well, theta, and then you have the prime form, and then you have this function G evaluated at some vertexes, then you have a product, and then you have a second term that you could also write in one integral if you like. Okay, so this is rather a very compact and simple formula. Okay, okay, so maybe let me just tell you about the contours, and then I will tell you more about the. So here is our surface, and so here are the packs of angle alpha, gamma, beta, delta, and so the contour C2 should contain all the alpha angles, and the contour C1 should contain all the gamma angles. Okay. So just to comment on how this formula is related to other formulas that exist in the literature, because there are many around, as I said. So it's probably the closest to the genus, so the one periodic weights of cheetah. So some of the really initial formulas that was found, which has this very nice product form as well. So if you want to, yeah, it kind of really has the same flavor. And actually, we inspired ourselves from the proof. The question was, what would be the objects when you have many parameters involved, and well, that kind of stuff. So there's also a formula in the paper of Berggren and Borodin. And so in their paper, well, anyway, Tomas will contradict me if I say something wrong. So part of the formula looks the same, but then in another part, there's like a pack that is not explicit, which is quite complicated. And if you would like to see the simple form, you would need to do a change of variable from there. I don't know if it's C2 to the Riemann surface to really see the simple part coming out. Okay, so it's like, yeah, it's like the other formula with a miracle change of variable that simplifies it a lot, for example. Okay, but this, we don't need to assume any periodicity on the weights to have this formula. Okay, and so how do you prove such a formula? Well, you prove k minus 1 equals an identity. You prove that it's an inverse. And so for this, you have forms G that are in the kernel. So that gives you zeros many times, but you don't want 0 all the time, right? You want to have ones also on the diagonal. Well, then you have the contours. You have to find the missing terms. So it's a lot about, yeah, having an idea of where you want to go, and finding the right object, the right contours, and everything. And then you use a complex integration technique, residue computations, and stuff to show that it's actually true. Okay, so here I wanted to make it explicit in the case where all the angles are the same. I don't know if it really helps. Anyways, that's the same formula in a specific case. Okay, so that's what I was going to say about the K-inverse formula. And now I want to tell you about the partition function. Okay, so the partition function was the determinant of this matrix. And so what we prove is an induction formula for the partition function, where the induction is on the size of the Aztec diamond, so an induction in N. Okay, so what are the notations? So here is the partition function with parameters alpha, beta, gamma, delta, so angle parameters here. And that's the value of the discrete Abel map at the point 0, 0, so left bottom corner. So by definition, this is the weighted sum of dimer configuration. And so what we prove is that if you take this partition function and multiply it by this term, which is, okay, you separate the vertices into odd, this should be a straight F, and odd vertices, boundary vertices, while you do some things with your vertices, then it's equal to the partition function of the Aztec diamond one size smaller with angles. So you have for each row and column, you have one angle parameter less. So here they go from 1 to n minus 1. And for the beta, they go from 2 to n. And then you also have to scale the discrete Abel map at the vertex 0, 0. And then you have another term coming out. Okay, so before going to the proof, why were we looking for an induction formula? So there's one of the first results, and actually our proof is inspired from that. One of the first results of the Aztec diamond was to compute the number of domino tilings of the Aztec diamond. And that's a very nice close formula is 2 to the n times n plus 1 over 2, I think. I will see it in a few slides. And that's a result due at least to Prop, but maybe to other people. And one of the proofs is by induction. And so this is kind of probably the maximal extension of this induction approach that you can use. Okay, so now let's specify this formula in some easier cases. So in G 0, so you have Kenyon's critical weights. Then you have you have a very simple formula for the partition function, 2 to the n plus 1 times the product of sinus angles, which using addition formula for sinus, you can write as this. Why I did this is not, it doesn't seem so interesting, but in the next slide, it will help to recover another known formula of the literature. You can specify even more as that all the angles are the same, equal to one equal angle. I mean, all the alpha angles are the same, all the beta angles are the same, etc. And so you get this even simpler formula. And then you can even ask that the beta minus alpha are all gamma minus delta are equal to 1/2. And then you recover the classical Aztec diamond counting formula. Okay, actually the scaling is different because we have weights 2 on the edges and not 1, but you can just scale out the 2. Okay, another corollary that you can get is there were weights in the literature that were around, which is like you take x1, y1, x1, y1, x1, y1, then z1, w1, z1, w1, then x2, y2, x2. So these are, I don't know, they're kind of weights. They can be parameterized in G 0. While there was we called it Stanley's formula because it occurred in a book of Stanley. You have an explicit product formula for the partition function. And actually, with the right parameterization, this is just this formula. Okay, so this is actually a direct proof of Stanley's formula as a specific case or a general formula. Okay, so the idea of the proof is the idea of prop. So I think it's one of my favorite proofs. Okay, it's the idea of prop using on top of it, the phase trisecond identity. Okay, so on dimer models, dimer graphs, there are two very important moves that you can do. It's the spider move, which is this one. So it's when you have a square, you replace it by a small square with legs. And then you have a contraction and contraction of a degree to a vertex or extension. All of these are, you can go in the two directions. Okay, and with these two moves, you can move around the set of all minimal graphs, actually. Well, whatever. They're kind of generic moves that allow you to go from one model to another. And so here on top of it, so that's in black, you have the moves on the graph, but we have to keep track of what happens with the train tracks. Okay, these paths I defined. So they do something a bit more complicated. So these are here in red. And so the key point of the proof is that actually these weights, these Fox weights, they behave well under these two moves. So if you have a spider move, the partition function changes by an overall constant. Okay. And if you do a contraction, it changes in this way. So you actually exactly control how the partition function changes when you do when you do such moves. And then so that's what we brought into the proof, is to see that this was what you really needed for it. And then it's the Fox props induction. So that's the way you see it on the graph. So you take you start from your Aztec diamond and you take 1/2 squares and you do a spider move. So this is what I've drawn here. And then now you see you have legs on the boundary. And if you have a dimer configuration, they have to be inside this dimer configuration because every vertex needs to be adjacent to exactly one edge. So this means that these edges have to be there. So you can take the weight and then you take them out. So then you take them out. I can take down all these vertices as well because they're already touched by a vertex. And so what you're left with is this. And then now you do a contraction here, 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 and you get an Aztec diamond, one size smaller. So I've drawn it from 2 to 1, but you can do it from n to n-1. Okay, this procedure works. If you start from an Aztec diamond of size n, you will get a nice, doing exactly the same thing, you will get an Aztec diamond of size n-1. And so since moreover, we know how the partition function evolves when we do these moves, well, that's how we get the induction formula. Okay, so you have to keep track of the train. It's a technical, but it's doable. Okay, so that's for the partition function. And now I will just show you some pictures. So about scaling limits, it was not the heart of our paper, but still we can say a few things. So the heart of this, where this was studied, was in the paper by Berggren and Berggren, and before in other specific cases. So we know k-1, so we know single edge probabilities. We can compute what is the probability of a single edge. And so there was a saddle point analysis that was introduced by Reshetkin Okunkov in 2003, and then worked again in Boutier, Chapuis-Cortel Ramasamy, and also used in Berggren and Berggren. And so with our formula, actually our formula is quite nice to do asymptotics on it. And so we can recover known results. So here are just the limit shapes. So like you see the different, the boundary of the scaling limits of the shapes. So this is genus 0, there's no hole. So we recover known results about this Arctic circle, Arctic ellipse, but also since we do not have, that's not what I would say here, but you also have more fancy shapes that were not known in the literature before because they do not come from generic weights. And usually in the literature, if you have genus 0, you want to have generic weights. It has some implications on the model. So here it's non-generic genus 0 weights. And that's in genus 1. So that was I think probably the first picture. But also we have some latitude and can handle non-periodic weights. So then you can have this hole that gets moved in different positions. So, okay, so this is what I wanted to tell about limit shapes. And yes, I think that I will stop here. And so thank you for your attention.
Thank you very much, Béatrice, for the Interesting approach, nice talk. Any questions?
I maybe have one small technical one.
Yes, Lorena.
There was an orientation of gray graph of the quad graph on some of the slides.
Yeah.
What is this? Yeah, what is this orientation of the gray edges of the edges of
Yes. They're all going out from the white. You know what? I don't know now why I've put this, because the alpha maybe, yeah. Because what you need is the alpha and the gamma paths need to be oriented. So these are, yeah, no, I don't, for what I said, you would certainly not need it at any point. Let's keep it this way.
That's fine. There is a question.
Yes.
Andrei, please.
Thanks. It was very nice. My question relates to the connections to complex analysis.
Yes.
On the scaling connection also to random planar maps and Schramm-Loebner evolution, and also probably a bit more gated. This is all on C1. Is there any extensions to Cn to several complex variables? How would this look in higher dimensions? Thanks. In higher dimensions in terms of complex numbers. Thanks.
Okay, so I'm not sure I understood everything,
Yes.
heard everything,
Okay.
but I can tell
Yes,
you,
yes.
so the random planar maps,
Sure, SLE. Yes.
yeah, or SLE,
Yes.
well, it's a different question. So random planar maps, so it's not, we're not doing random planar maps because in a random planar map, you draw your graph random on your map with some I don't know, quadrangulations or whatever kind of maps you're interested. And we're fixing a lattice, okay? So I think, of course, you have this random planar map community, and then the community of people working on lattices, fixed lattices. And we're very interested in the results on one side or the other because sometimes they look alike, but the techniques are very different because, well, it's really different when you sum over all the maps you can get, or when you fix and the configuration, you kind of have a double randomness, okay? And when you do random planar maps, when you put a model on a map, and in our case, we fix the lattice and then we put a model, okay? So it's very different techniques, very different kind of results and stuff. Okay, so what is something that is easy on one side can be very difficult on the other, and vice versa. Connections to SLE. So SLE is what you would, it's as much in my talk as in Tomas's talk. You don't really have an SLE here. When you have such a picture, when you want to see an SLE, what you have to do is to put some boundary conditions so that you have a path going from one boundary to the other, okay, which is not exactly the case here. And then when you have this, so in the dimer model, you would expect a convergence to SLE4. So it's a specific universality class. Okay, and so basically when you have the Gaussian free field, so in the regimes where Tomas said you have the Gaussian free field, you would expect to have an SLE4. In the frozen regions of stuff, you wouldn't expect SLE, okay? But then you have to tune your model appropriately to see the path, okay? That's a good answer of SLE. And then now, if you take weights with values in Cn, so that was your question, weights not in C, but in Cn. I don't know. So there are some works on dimers with quaternion, okay, weights.
Yes.
So then you have matrix, yeah, and then you need to introduce connections, and So yeah, there are some works in this direction. I'm not sure it's exactly to the generality you're mentioning, but yeah, so there's work by Kenyon and then Kessel and I can't remember who, but that's two authors that worked on that kind of stuff. But it's for sure not with Fox weights and that kind of stuff. Yeah.
Thanks. I will check. Thanks.
Okay.
Thank you. Any other question? Mariano? Well, okay. If not, I think it was a nice afternoon in my time zone. And thanks again to both speakers. Very interesting talks. And we resume next week because, yes, next week is a seminar, probability seminar. And thank you all for participating, everybody, and the speakers again.
Thank you.
Thanks a lot. Bye. Thanks.
Bye.
Thank you. Thank you. Ciao, ciao.
Thank you.